what we're going to be going over here is we're going to be looking at how Lagrange multipliers work, and we'll look at it from the visual perspective. Now, we'd be using the Lagrange method here, these Lagrange multipliers in constrained optimization here. And our example here would be based on maximizing some output or some utility here. Now, we're going to look at it in terms of a production function here, which is really similar to the Cobb-Douglas production function. Okay, so this is our production function here, and we don't want to get lost in our equation here, but we'll just use it as a reference here. So we're going to have to maximize some Q or output here or some profit, and it's going to be based on some revenues here. I've got a certain amount of revenue per unit times some material times some labor quantities that we're going to use, raised to some exponential amount for each of those here. So that's our revenue portion, but then our spending our cost constraint is shown over here. We got a certain dollar amount here for material, less a certain dollar amount here for labor, and this is all on a per unit basis. Okay, so what we have to do with this production function here, or our function, we have to break it down here. So what you're doing with these Lagrange multipliers, again, you'd have to break their function down where you're going to maximize some revenue, the revenue portion here, and it has to be subject, and that would be F function here times some material and labor here in our profit function or our revenue function here, and then we'd be subject to some cost or budget constraint here represented by G times a function of some material and labor inputs, and that we'd have a cost here, a certain cost amount here, that would be our budget, and then it would be based on, it would have to be equal to a certain amount of a dollar amount of labor and material here, and this is our constraint. Okay, so the first thing we want to look at here, and we'll look at it in 3D here. Since I can't rotate this around here, we'll just look at it from the several different angles. So what we have here, I'm showing our QR output here, that would be our revenue showing up along our vertical axis, and then just looking at a side view here of our production function here. I'm showing that with these isoquant lines here, this sort of bluish silver. That's our production function. This is what we're going to be working with, and that would be that $1,400 per unit times some labor and material based to some exponential amount. But the key is here, what we really want to look at and get an idea here, what we have to deal with is we're going to have what they refer to as some vector field for our Q or output, and that's really the direction and magnitude of our output or our revenue that we'd be looking at a certain point. So what's really interesting about this is you don't have to go and try to understand all these equations. We're going to be looking at it from the visual perspective. So the idea here is, and just looking at it again from the side angle, oh, and yeah, this yellow thing here is an iso curve, or that's our output level, where it slices through our production function at a certain output. It looks at about 60,000 here in Q or output here. So the idea here is you look at, plotted it out here with these arrows. So the idea here is you look at your arrow here, and it gives you an idea where you're headed with this production function here. The bigger the arrow, the greater the output, and also the direction that it's pointing in here. So it's really a little hard to look at here just from the side angle, but the idea is you see here a big arrows up here where we have the greater output here, and then in back here you'd have some lesser arrows or lesser size of arrows pointing in different directions. Okay, so that's the idea what you'll be looking at here when you want to analyze this visually. So let's go over and let's just look at it here in the case here where we're looking into this production function. Again, we got our iso curve here, or our output curve here, or slicing through our production function here shown in yellow, and then you can look at it from the perspective here. Again, you see those arrows here, that big arrow here, it's pointing in the direction of the greatest output. So you can see right here, you can see, move it up here, and it's really sitting out here. It's material and labor here are shown at different amounts. It's at the greater amount here for your material and labor that we're looking at in this case. So you can see it's pointing up here, and it's way out away from our origin here. And you can see the smaller arrows, and they're pointing in their direction. All seem to be pointing in a direction here, in this direction here in a production function. And just looking at it in the top view here, so it's a little hard to see it, but the bigger the arrow, the direction it's pointing in, because these are 3D arrows here, that's where at that very point, that's the output that you'll be looking at. So you can see farther back here, smaller arrows here, and off to the side here, smaller arrows. So somehow in this direction we're looking at the greatest output. So if we look at it one more deal here, again, these are also these yellow slicing through our production function. That's our ISO, our equal product curve here, or equal output curve here, and that's really based on the level of Q that we have here for a certain output or certain output that we're looking at. In this case, it would be revenue here based on our production function equation. Again, just looking at it from this angle here, you can see those arrows here, real big, and they're pointing in this direction here at a large, greater the increase in Q of your output, it'd be the greater the arrow, and then it depends on it points in the direction of our greatest output. So you can see those big arrows where they're pointing in that. So if you had something like this, you could just rotate it around and pretty well get an idea what you're looking at, rather than just looking at some equations that you have to deal with here. So that's what we're trying to do. We have to make some sense out of these what they call this vector field or output here. And then again, this isn't based in 3D, and it's based on our material input, labor input, and then our output here, that based on our material and labor inputs. Okay, so that's what we have to deal with, this vector field. So let's move up here now. Now this is the case here where we're going to turn that vector field into a gradient field, and that's at a specific output here. Remember those ISO curves we have shown in yellow here? We have a specific output here based on our production function. So that gradient field that we're showing, and these are those red arrows here. I'm just showing them in red arrows here. That is turning our vector field, those vectors, those 3D arrows that we looked at, into a gradient field. And a gradient field is exactly at that ISO curve. And this is where you're looking at the magnitude and the direction here of the greatest or output here, or the most efficient output here. So that's what these red arrows represent here. So you have these gradients. This is what we have here. We want to determine the direction of that production function here and the magnitude, the greatest output here at the point. And really we're going to find it's going to be following up this sort of yellow arrow here. That's where our gradient is going to be here. We're going to have the greatest increase at that point. So that's what you're looking at here. These red arrows, we turn those vector field into a gradient field, which is giving us our maximum output here at a certain production level. But what we have here, and let's move over here. So this is the case that we have to deal with now. We got our production function. Remember we talked about that shown here with those ISO curve lines, the blue deal here. That was that 1,400 times dollars per unit times our material and labor inputs raised to an exponential amount. So I'm showing this, that's our production function here with the ISO curves or equal product curves. And this here, this yellow one again, was really our ISO curve here that we have at the specific output. I think it was like 60,000, Q here at 60,000. But the key is here. Here's these little red arrows here again are our gradients here. Those represent our gradients, and that they're pointing. Maybe let's move back over here. Okay, so let's move over here. One thing I didn't mention, those gradients, they're really pointing in the direction here of the greatest output or most efficient use of our material and labor here. We're going to get the greatest output. They're pointing in that direction at that specific point that we're looking at here. And again, they're supposed to represent the greatest output in a specific direction at, in this case, the specific ISO curve here. But then moving back over here, this is where this is where our Lagrangian work comes into effect here. I'm showing it here. Remember, those are these are our gradients, these arrows here. But they come up against the constraint here. The constraint is that amount of labor, our budget of material and labor. A certain unit amount, in this case we had $350 per unit here for material, plus $200 per unit here for labor, for each unit that we use here. And that is our constraint. So we come up based on our vectors here for our Q, our output here, at a specific level here. This is where we come up against this constraint. They come up bunting up against the constraint. The constraint is that spending constraint. And I've got that slicing through our production function here exactly at our ISO level here. We have to come up against that. So we can't exceed that. So that's the key that we're going to be looking at. So the idea here is these gradient vectors here, they're all the production function's first derivatives here. We don't get into that technical work here, but that's what we're talking about. So this is what we're going to be looking at, coming up against the constraint, and based on that constraint at the specific output level, we know our gradient at that particular point, and then we're going to be able to determine the exact output here, or requirement for material and labor, and our based on our unit revenue per unit here, we're going to come up with the most or the greatest profit here based on that. So that's what we have to deal with, and we're going to go and we're going to try to get an understanding of how we use this Lagrange multiplier and how it becomes useful here in solving our constrained optimization here to maximize our output. So we'll continue on. Okay, now to determine our Lagrangian multiplier. So we'll start with our reference here where we're looking at those gradients here. Those are those directional arrows here where they show the direction here, the greatest increase here in our production function. And really you're looking at it, this is where you have the steepest direction and the greatest magnitude, and these gradients here, these red arrows here, are really perpendicular to our iso cost line. We have this iso path line here, and those gradients are perpendicular to it here, and really they represent the maximum direction here with the maximum output in this case. Okay, so let's go down here and now let's throw in this cost constraint. So we have our iso curve here, and we throw in our cost constraint here based on our material and labor constraints here. So now let's go and let's understand this Lagrange multiplier. Okay, so looking at really a top view here, and we're going to be looking at first here, looking at our iso path here. So that's an equal product curve. So at that production level that we have here, we have set up this iso path here, and it's a little hard to see with the steepness here because we're looking down on it. But what you want to do here to understand this here is you take, at some point here on this iso path, you're going to follow along until you hit some maximum point here. So you start out here, and you're going to have you're going to keep increasing and increasing your slope here. You're moving higher and higher here on your product function here, or your output function here, and at some point here, as you move along that curve here, you're going to reach some maximum amount here, shown by this red arrow here. Then as you keep on moving along the iso curve, you're going to keep reducing. Your slope is going to actually decrease here. It's going to decrease here. So the key is here, you want to move back. When you start decreasing, you want to move back here to your maximum point here, and then if you keep moving back here, then you're going to actually be reducing your slope here. So you're going to, there's some maximum point here where you keep moving left to right or right to left here. You're going to hit some maximum point here, the maximum steepness in your slope here. So this is the case here. You're going to have your slope is going to be at your maximum. You're going to have some establish some tangent line or tangent point based on your iso curve at that point, and that's your maximum slope here that you have in a curve. Again, it's a little hard to see here. You would think that maybe you're levering out to zero here, but this is where you're getting your maximum slope here based on your material and your labor input here. Okay, so we looked at our iso curve here. Now let's go over here and look at our cost constraint. Now this is the case here, which you're going to do the same thing here. The idea here is the goal is to climb as high as possible, but you can't move any higher than your constraint here. So this is our production function. We have our iso cost line shown in those red lines here. And again, as you move up in this direction here, you're increasing your output here. So if you look at your cost constraint here, it's slicing through our production function here. This looks like it's very steep here, but the point is here, you're starting out at a lower iso cost line here, and as you move up through those iso cost line, you keep increasing and increasing the slope here. So you keep moving along, so you reach some maximum amount here as you move up along your iso cost line or your constraint line here based on those iso cost curves. Then you hit some maximum amount, and if you keep on traveling along your iso cost or your cost constraint here, you're going to go down here. Your slope is going to keep increasing. You're going to have a lesser and lesser slope here. So you're going to be reducing your slope. So the question is here, you really want to move back. You want to move back to that maximum amount here. And then had you kept on going in your from left to right here, you've been reducing your slope here. So you're going to have some maximum amount here based on that cost constraint. There's going to be a tangent line or a tangent point here based on the change of slope here. So you're going to have some maximum point here. Okay, so what you're really looking at here, the slope, this is the key here, the slope of that constraint line that we have equals the slope of our level curve. So over here we had our level curve here, and moving back here we had that slope here. That was our maximum slope here in the level curve as we moved around it. And then over here we had our cost constraint slicing through our production function as we met some maximum amount here. So the question is here, really, this is a case here where your constraint slope here, your constraint, and your isocost slope here are the same here. That's where then you have reached your maximum amount here. Okay, so the logic is this here. When the level curve, that's our production function here, and the constraint, that is our cost constraint, have the same slope, the maximum has been reached. That means that they're parallel, and at that point, parallel at that point that we have that maximum slope point here, and they're in the same direction. That tangent line, and they're in the same direction here. And what we're saying here is the gradients are always perpendicular to the level curves. So if these two curves are parallel, their gradients must also be parallel. That means our gradients of our production, or of our revenue function here and our cost function, at some point they're in the same direction, and they differ only by a scalar Lagrangian amount here. Okay, so if we looked at our Lagrangian equation, it's this lambda, it's the Greek symbol here for lambda. Gradient is this upside down sort of V here. And just for our production function really equals our cost function here. That's our output here, that F, the gradient, that's our gradient symbol here of our output function F here based on material and labor inputs equals the Lagrangian, or our lambda here, or our Lagrange multiplier here. That symbol here is our Lagrange multiplier times the gradient here of our cost function. That's where you're going to have your maximum output. The gradient here, your production function, equals the times your, you got this Lagrange multiplier here, times your gradient here of your constraint here. So, and then just rearranging those equations here, so you take and just move this, your lambda times your gradient here of your constraint over to this side of the equation. They're going to, you set them equal to 0. And then if you do some more manipulating here, your Lagrangian here equals your production function minus your lambda, or your Lagrangian here times your gradient, your cost gradient here minus your cost here equals 0. And that's, again, subject to your cost constraint here, not to make confusing here, but you reach your maximum subject to the constraint here. Just understand that. So if we go over here, just to get an understanding here visually what we're talking about with all those equations. Remember, this was our isocost curve here, and then at that point here that we had that same slope here, they're parallel. We have a maximum point here, the tangent line, or that tangent point between our cost constraint here and our iso curve. They met and they're equal here. So what you're doing here, and we're saying that our gradients here, these yellow ones here represent our gradients here for our production, our revenue part of the function here, and our cost part of the function. G of x here would be our cost part of the function here. F of x would be our revenue portion of the function here. Those gradients are parallel because they have to be parallel because they're perpendicular to the iso curve. They're perpendicular to the iso curve. So the iso curve here and our cost function they share the same parallel line, or the same slope here at that maximum line, that maximum point here. So there is really a difference, and that's what we call the Lagrangian multiplier. They differ by a scalar amount here. Our cost constraint here, or the gradient here for our cost constraint here, versus the gradient here for our revenue part of the equation here. There is some difference in amount here. and that difference here is the scalar amount. Okay, so now we can just continue on here and just wrap it up here by just looking at the difference between our cost, determining differentials or partial differential between our cost function and our output or our revenue part. All right, now we'll go over and we'll make our calculations here. So remember, the gradient is just a vector that collects all the function's partial first derivatives, and it just puts them in one place. So the question is, why did we actually add in this Lagrangian here, or this Greek letter lambda here? Could be any variable here, but we just refer to it as lambda here. You do it for really two reasons here. You do it because you're going to have to solve your equations here when you're dealing with multivariate calculus, as we are here. You're going to have to add in an artificial variable here to solve your equations, and it also gives you a multiplier effect. So we added in our lambda, this artificial variable, to include that constraint. And our solution now will be able to come up with an exact solution for, in this case, our material and labor. And really, it eliminates the x in terms of y solutions. So our x would be like material and y would be like our labor here. And we want to come up with an exact amount rather than x in terms of y. So you end up with three equations, three variables, or three unknowns here. So you can really have a three-step procedure here. So let's go through that. So for the first step, you set up your Lagrangian equation. So in this case, remember, we're dealing with that revenue or output here, certain units here, and revenue per unit times material and labor quantities raised to some exponential amount. So that would be our objective function here as far as our revenue or output, and just in terms of Q here. And then we'd subtract from it our cost, or our, in this case, the budget constraint. So our cost here, we had a certain $350 per unit per material for per unit here, and then $200 for labor. So you have a minus those here. You subtract those from your revenue output here. And then you also, this is where the constraint comes into case here. So we're constraining ourselves to a budget here of $40,000 for material and labor. So this is how you set up your Lagrangian. Just take your revenue or your output units here, and then subtract from it your cost or your budget constraint. In this case, this is where you add in that Lagrangian variable here, this artificial variable lambda here. And then remember, you're subtracting this budget or this cost here from our revenue portion. So we'd have a negative sign here, add in your Lagrangian or your artificial variable here, times. Then you take it times 350 for material plus 200 for labor, and then you subtract from it your cost constraint, that $40,000 in this case. So that's our Lagrangian equation here. So then you just find the gradient, or you take the partial derivatives of that Lagrangian or vector function. I'm not going to go through it all here, but I just stuck it into, in this case, I use MapleSoft, so just understand what's going on here. So our partial derivative with respect to our material here, and then you're going to see where this Lagrangian came in. So you subtract, then you have your partial derivative for material here. Then you subtract from it the material quantity here. That it did it automatically here when we did our derivatives here, or we did our gradient here on that Lagrangian function. So you have 350 here for material. Just understand it, times the Lagrangian multiplier, that artificial variable. Then you add to it the partial derivative here with respect to labor, and then you subtract from it, and then the labor cost here, just understand that, times that Lagrangian multiplier here. And this is really a vector we're looking at for material, labor, and then you add to it the cost constraint here, minus 350 in material, minus 200 labor, plus 40,000 here on our cost constraint. Now just remember, the computer had solved this for our vector here for material, labor, and then this is also our lambda vector here. It's a little hard to see. And that's our step 2. So now for step 3 here, we set each partial derivative equal to 0 and solve the set of equations. So again, the computer has done this, software package has done it. Just take, you can see what's going on here. Just take your gradient, or your partial derivative here for material, just bring that down here as it is. It's already set up here. And then for labor, same thing. Just take that down here. And then for material, same thing here. Now just remember, the lambda is sitting in here, or that artificial variable for your partial derivative for material and your labor. And then you'd have your cost constraint. You'd be subtracting that out here, just as it is. So then these three equations, three unknowns, and the computer solved it here for labor, equals to 78.049 here. units of labor, and then material 69 point some percent of here material, and then that artificial variable lambda here, our multiplier here, 0.096608 here. So this is key here, this lambda. We used it for solving adding our constraint and come up with 3 equations, 3 unknowns here, and we're also going to get the benefit of this multiplier effect that we'll look at. So let's just go look at that briefly. Okay, just moving up here again, looking at this red, I'm showing at our production function here, so this greenish blue here, that was our constraint here. And then we have that output, or that level, at that level here, the green here was our level output here. And then that little red dot, that's our actual value here that we solve for, our maximum output based on our Lagrangian here with our 3 equations and 3 unknowns here. But this red line here, that is really our gradient path. This is the path here of maximum output. It's really the direction in maximum output is based on that red gradient path here. And that, again, the computer had put in here. Okay, so we just get a pictorial view of that. So if we just go down here and look at our lambda here, just to briefly understand that, our multiplier effect, remember that here, 90.9608. So let's just say this Lagrangian here is a scalar. That's really what it is a scalar here. So just say our constraint here, remember we set our constraint here, budget constraint at $40,000 here, and then based on that 40,000, we actually had an output here for our production function at 47,125. Now let's move our constraint up here to 40,010 here. So we just increased it only by $10 here. So now our output is gone from 47,125 to 47,135. Now that is an actual calculation here. So we increased it by 10. Our output is gone up approximately by 10. And this is where that multiplier comes into effect. So remember 0.96, that 6.08 here times that increase here, $10 here, that increased our output, 0.966 here. So that's where the Lagrangian comes in as a multiplier here, just to briefly understand it. Okay, so that'll conclude our discussion here on the Lagrangian multiplier and basically how it works.